Welcome to Sundar's lecture. This is lecture number 82, and in this lecture we are going to see basics of coupled coils, which means we are going to see what is dot convolution and how we are going to write the KVL expressions for dot convolution or coupled coils. See what are all the topics we have seen in the previous class. See, we have taken with the magnetic basics of magnetic circuits, and that we have seen what is self-inductance, and then what is the mutual inductance, right? Mutual inductance will be same, right? Whatever it may be. If you exit coil 1 or coil 2, the mutual inductance value, it will be N1, N2 divided by S. It is a constant value, right? And as so that uh, self-inductance value is also a constant value. This is also a constant value, right? So, for example, if you further simplify this, or you can write from this expression itself. So, L is equal to N into pi by I. This is the expression we got, right? See, what we have taken here, the ratio of pi by I, that is nothing but we have taken it to be constant, right? Term this term is a constant value, right? So then what happens? What is n? N is the number of turns, right? N is the number of turns in the coil number 1. Here we have only one coil. So what is the point is L is also a constant value. L is also a constant value. If you further simplify this, you will get L square divided by S. You just simplify by yourself, substitute the values, of for example, you put pi is equal to b into a, and for I is equal to, right, maybe I will write here. So you substitute pi is equal to ba, this is the formula, and instead of I, what the uh, what is that? The formula for magnetic field intensity H is equal to Ni by L, right? Ni by L. So what you do, you just substitute I value as HL divided by N, and you substitute both these two expressions here, and also the value of B, you can write it as mu H, and also those kind of things. If you substitute and you simplify, you will get N square by S, this value. So this is also a constant value. That is the point you have to understand here. Anyhow, see, today's topic, it is basics of coupled coil. See, we know these kind of things, right? If you, this is I1 and whatever it may be, if you excite this coil, the pi M1 will be generated. This is N1 turns, this is N2 turns. So if pi M1 came here, then obviously the EMF will be induced in this coil due to the excitation of this coil. So mutual inductance will come down, right? So for example, for these kind of things, what is the voltage of this coil? Voltage of this coil V, maybe I will write it as E1. E1 will be is equal to whatever it may be. It is self-induced EMF, right? What is self-induced EMF? It is N1 into d pi M1 by dt. That's all. No other term will come here, because this coil is not excited. If this coil is excited, then this coil will get the induced EMF. This coil will get the mutually induced EMF, but this coil is not excited. So, which means I2 is 0 here. I2 is 0. Even if I write this, you will not get down. Right? If this is E1 and I am writing this to be E2, I know what is E2 value. What is E2? What is E2? There is no current flowing through this coil, because I have not excited this coil. So self-induced EMF will be 0. And what will be the mutually induced EMF? It is M into d pi M1 divided by dt. Can you understand? So this is the value. Not, oh sorry, I made a mistake. See, this is di1 by dt. This is di1 by dt. So we are writing this value, right? EMF value. So this is di1 by dt, since the first coil is excited, mutual inductance, right? So this is the formula. Anyhow, now hereafter I am not going to draw the diagrams like this. For example, these coils can be drawn like this, drawn like this. First coil, this is first coil, and this is second coil. See, the thing is, we are going to tell the dot convolutions now. For example, this is dot and this is dot. For example, you take for an example, and if it is so, so what is this one now? This coil will have self inductance L1. For example, if I have excited this coil also, then I will have an inductance L2. That is self inductance, right? Then this both coils will have a common mutual inductance. That is the point. That is the point. See, if I excite these two coils, then also I will get the mutual inductance to be a common value for both coils, right? So if this is so, then what will be the induced EMF? One, what happens to the mutual inductance if you are going to write the values, right? For that, what I will do, I will draw the diagram. Either these coils should be connected in parallel or this coil should be connected in series. So first, what we will do, we will take a series connection, series connection. So in series connection, for example, we want to draw this diagram like this. This is the diagram. Let this is be the diagram, right? This is excited with the V of t. Maybe we will take like this. So this is now dot. This is now dot. For example, if this current is I, then obviously this current should be also I, since these coils are connected in series, right? So what is the thing here? See, this coil will have L1 and this coil will have now L2, since both coils are excited with the current, and whatever it may be, the mutual inductance for these two coils, because this is coupled, then this will have a mutual inductance, right? So that is the whole point. For example, if I want to write the V of t expression for this connection, then V of t, I am writing KVL expression. V of t will be is equal to, see, this coil will have self-induced EMF, and also this coil will have mutual induced EMF. And whatever it may be, see, be very careful, listen carefully how I am writing this expression, because this will help you to solve all the problems related to coupled coils, right? So from here, I am going to write what is the self-induced EMF. Self-induced EMF, which means what, the self inductance L1 multiplication of d, whatever current flowing through this coil, di1 by dt. See, try to understand one thing. I always write self-induced EMF in the positive value, in positive. I never write the self-induced EMF in negative value. So this is self-induced EMF. So this is self-induced EMF. Then what I have to write? I have to go for mutually induced EMF. See how I am going to write the mutually induced EMF now. Since this coil is coupled with this coil, I have a mutual inductance. So what I need to do here? See, this current, this I is entering through dot in this coil, right? And also you have to consider the second coil, what current and in which direction it is going. See, this also, this coil, the current I is flowing towards through the dot, right? Both are same, both are same. This is also going through dot, this is also going through dot. So what I have to do, if it is so, then I have to put plus, and whatever the mutual inductance I have given with, then I have to write what is the current flowing in the second coil, because I am writing mutually induced EMF, right? So second coil, what is the current here? It is di, not I1, sorry, I have made a mistake here. This is not I1 because it is I, right? It is I. So this is di divided by dt. So this is mutually induced EMF. I have written for, this is for first coil. This is for first coil. Try to understand. This is for first coil. Then I have tried the second coil. So if I am going for the second coil, see, I will write it down. Second coil. Straight away I will put plus, because for self-induced EMF always you put plus, right? So what is the value now? it is L2, it is L2. What is current flowing in this coil now? I don't need to see what is the current direction in this coil, where it is going. No, you don't do anything. Put L2 into di by dt. Simply you do this, right? For self-induced EMF. This is for self-induced EMF in coil number 2. And what you do now, you have to see for the mutual induced EMF. For mutual induced EMF, you have to see the directions of current. See, in this coil, the current is flowing through dot. And also in this coil, the current is flowing through dot. Then what will you get here? You have to put plus, and whatever the mutual inductance I have here into D, what is the current flowing in the first coil? What is the current flowing in the first coil? This is di by dt. And this is now mutually induced EMF. Right? So this whole area is for second coil. Second coil. This is the whole thing. So now if I write V of t will be is equal to, see, the di by dt is a common term. Take if I take di by dt commonly outside, this is L1 plus this is M plus L2 plus M into di by dt. This is the final expression. So what I will get if I write it down, I will write in the next page. See this one, V of t can be written as L equivalent of di by dt. Di by dt. I have just taken this to be L equivalent. And what is the value of L equivalent now? What will be the value of L equivalent? L equivalent will be is equal to L1 plus L2 plus 2m plus 2m. That is what I have here, right? This m will be added. So this is the L equivalent for two coils connected in series, and you see I will say this is aiding this coil, this topic. I will say it is aiding. Why I am saying this is aiding? Why I am saying this is aiding? Because this current is flowing through dot here, this current is also flowing through dot. So what I will say, if two coils are aiding, this is the equivalent inductance of the circuit of the two coils. Now what we will do, we will take another one now, that is opposing. What happens if I am going for opposing? Simply you draw the diagram now. So I will take the diagram. See, two coils are connected in series like this. Same thing, same diagram. No difference. You try to understand. Right now, this is the diagram. Two coils. This is again V of t. No difference in this. And this coil current is I. See, in series connection, current will not change. You know those kind of things, right? So now this is dot and this is dot. And what happens now? If coil is excited, then it will have self-inductance. Then this coil is also excited. Then also this coil will have self-inductance. And both coils are excited. Any one thing, it may be the mutual inductance will be there. And now we need to write the expression. How will you write the expression? Same way, I'm going to write the KVL expression. That is V of t will be is equal to. I need to write the self-induced EMF for this coil. Now I will go first. Now I have to write the self-induced EMF. See, simply for self-induced EMF, you don't see anything. Put plus values, right? In plus, what is the value now? It is L1 d. What is the current flowing here? It is di by dt. It is di by dt. Simply you can write. And I have to see for mutual inductance now. You should see what is the directions of current. The current through this coil is entering through dot. But what happens to in this coil now? The current will leave this coil will leave the dot through. In this coil, the current is leaving the dot here. Try to understand. Not entering, it is leaving. So if it is so, then what you need to do, you have to put minus and you have to see what is M mutual inductance, and D, what is the current in the second coil. See, here both currents are same, so no problem. But if currents are different also, you have to write what is the current in the second coil. This is di by dt. So I have written for coil number 1, I have to go for the coil number 2 now straight away. If you are going for coil number 2, don't see anything, put plus the self inductance, that is L2. What is the value? It is di by dt, simply, right? Then I have to see for mutual inductance what is happening. See, through this, in this coil, through dot the current is leaving, but in this coil, through dot the current is entering. So it is opposite. So I need to put minus m into d, this coil current, di by dt. Here both are same. That's all I have written, right? So for both coils, I have written the self-induced EMF and mutual induced EMF. And if I further simplify this, what I will get, um, maybe I will write it in a different color. So V of t can be written as L1 plus L2, maybe this value, L1 minus M plus L2 minus M into di by dt. So finally, if I write this one, I can write V of t, which is equal to L equivalent of di by dt. Right? What is now L equivalent here? L equivalent will be is equal to L1 plus L2 minus 2M. It is minus 2M. Try to understand. Right? So this is the L equivalent if two coils are opposing. If two coils are opposing. Opposing means what? That is why this dot convolution is very important. See, the equivalent inductance value will differ here. That is the whole idea you have to understand, right? So now we know what is the series aiding and series opposing and what will be the expressions, right, for L equivalent expressions, right? Now what we will do, we will go for the parallel aiding and the parallel opposing, right? What happens if the coils are connected in parallel? See, I will write the title. It is parallel aiding. What happens if parallel aiding? What is the diagram we will have? See, this is the diagram, right? This is the diagram, and we have coil like this. Two coils, are connected in parallel. And connected in parallel in both coils. I have taken this is dot and this is dot. And what happens here? This current is I. This current is I. And what is this? This current is now. I will take this current as I1. And what will be this current? Simply. See, if you apply KCL here, this current will be what? I minus I1. That's all. Simply I will write, apply KCL here so that you will get what is the current in this coil. So obviously this coil will have self-inductance and this coil will have self-inductance here L2, and whatever it may be. If these two coils are excited, then obviously you will have mutual inductance, right? So I have written this is V of t. This is V of t. So what I am going to write now? I am going to write the KVL for this loop, for only this loop, and I will write the KVL for this loop. I will get the values. What is the my ultimate aim? I need to find what is the V of t value with L equivalent di by dt. Since this current, this coil is excited with a V of t and current flowing here, it is I, right? So I need to write what is the V of t expression now. So L equivalent, I need to find what is the value of L equivalent, right? So how are you going to find? So write the KVL for this loop and then for the second loop. So I am going to write KVL at loop 1, right? So if you are going to write the KVL, then obviously what happens now? V of t will be is equal to, see, I will write the KVL for this one. So what happens here? See, I will have only one coil, so I have to write what is the self-induced EMF and what is the mutually induced EMF. So if I am going to write what is the self-induced EMF straight away what you do? You put L1 into D. What is current here? It is di1 by dt. di1 by dt. Don't see anything. You put plus L1 di1 by dt. And you see, now I have to write the mutually induced EMF now. See, through this coil, the current is entering here. But through this coil, current is also entering here. This is also entering, this is also entering. Current may vary, but through dot, the current is entering. Through dot, the current is entering. So what I have to put here? Put plus mutual inductance M. Here D, what is the current flowing in the second coil? Try to understand, right? That is D I minus I1 by dt, right? So if I further simplify this, what I will get, V of t will be is equal to L1 di1 by dt, and then plus m into di by dt, and then if I multiply this one now, minus m into di1 by dt, so I will get an expression like this, so we make this expression number 1. Now I am going to write the KVL for loop 2. Maybe loop 2 in sense I will write KVL for this whole loop, outer loop. Maybe I will write here outer loop. So outer loop, what I will get now? Again same thing, this one, right? This one. So V of t, I will write for V of t, which is equal to, I need to write what is the self-induced and mutual induced EMF here. So self-induced EMF, obviously whatever current flowing through this coil, L2 into this current, di minus I1 by dt, that is self-induced EMF. No problem with the self-induced EMF. And you have to write the mutual induced EMF. See, mutual induced EMF, this coil current is entering through dot. This coil current is also entering through dot. So what you will get? This is plus m into d, this coil's current, that is I1 by dt, right? So if we further simplify this is V of t. If we further simplify this, L2 di by dt is one term, minus L2 di1 by dt is the other term, plus m into di by dt. This is expression number 2, right? This is expression number 2. And see, both expressions are same, V of t, V of t. So what I can now do, 1 can be equated to 2. And what I will get now, if I further write it down, maybe I will put this one here. See, if I do so, then I can equate these two expressions. So this is L1 di1 by dt, and then plus m into di by dt, and then minus m into di1 by dt, and that will be is equal to L2 di by dt and minus L2 di1 by dt plus m into di1 by dt. So what you do now, you just take I1 terms one side and common I terms to the other side, right? I will take it to the next page. So now you see, I have just taken out, I have just written I1 terms one side and I terms the other side. So if you take I commonly outside this in this one, so this is L1 plus L2 minus 2m, right? Minus 2m into di1 by dt, right? That is the one term, and that will be is equal to, if you take the I terms, this terms commonly, this is L2 minus m, this is L2 minus m into di by dt. That is the whole idea, right? So if I want to write what is di1 by dt, di1 by dt will be is equal to L2 minus m divided by L1 plus L2 plus, not plus, minus 2m this whole term into di by dt. Why I need to do this? See, try to understand. I have to replace this one, right? If I substitute in this expression V of t, instead of this di1 by dt, terms of I di by dt, so that I can easily get this one. So that I will get a real equivalent. That is why we are doing these kind of things. So I will take this expression, so that I can substitute in this expression now. So this one, this expression, this is the expression, right? So now what I will do, I'm just going to substitute in this expression, right? di1 instead of di1 by dt, you just change this one. So v of t can be written as now L1 into, instead of di1 by dt, you substitute this one, into L2 minus m divided by L1 plus L2 minus 2m, right? Minus 2m into di by dt, into di by dt. That is for the first term, and plus this term is already di by dt. This term is already di by dt. So I don't need to do anything. Then I have to put minus m here, di1 by dt, right? So this one will be L2 minus m divided by L1 plus L2 minus 2m into di by dt simply. Right, now what you do? You just multiply and take di by dt commonly outside, di by dt commonly outside, and you see I have to multiply this one, right? So L1, L2 minus m minus sorry, not minus m, minus L1 m divided by L1 plus L2 minus 2m, this term multiplication, I have taken di by dt outside, and then plus m will be there because I have taken di by dt outside, then plus, and I have to multiply this one, right? L2 m minus this term, this term, this is minus, right? So it will be minus plus, I have put plus, so this is minus L2m, and then plus m square will be there, plus m square will be there, and then divided by L1 plus L2 minus 2m, right? So this term. Now you see the common terms, this term and this term has a common denominator. So I can write like this, right? So it is di by dt, di by dt. This common term, this is L1 plus L2 minus 2m, and I can write this one, these two terms, L1 L2 minus L1m, L1m, and then here minus L2m plus m square, plus m square, right? Then this value will be plus m, will be plus m, right? So now what I can do, now I can multiply this term here with the I can take LCM simply. So just I have taken this to the next page, and you see now here I will take LCM. So what happens here, V of t will be is equal to di by dt is there, di by dt is there. So this term I will take LCM. So the denominator will be now L1 plus L2 minus 2m. So this term, this is divided by 1. So cross multiplying this one, this will be same, minus L1m and then minus L2m plus m square will be there, and if I take LCM here, this is plus, I have to multiply, right? So L1m plus L2m minus 2m square. So what happens here? This term, this term, this term, this term will be cancelled out, and finally if I write the expression V of t will be is equal to this term L1 L2, and if I minus these two, this is minus m square divided by L1 plus L2 minus 2m, this whole term, multiplication of di by dt. See, I have got this one, I have got this expression, right? So di by dt, right? Anyhow, I have written this as capital letter I, but it is small letter I, right? Small letter I. So I have got this expression like this. See this one. So what is L equivalent here? What is L equivalent? So L equivalent will be is equal to, this is L1 L2 minus m square divided by L1 plus L2 minus 2m. This is for parallel aiding, parallel aiding, right? So we have found this value. Now what is my point? My point, I let it to you people, please do by yourself. I am not going to derive the other expression. What is that one? See, if this is parallel aiding, if this is parallel aiding, then you have to go for the parallel opposing. So I will draw the diagram anyhow. See this is the coil now. I will write the title parallel opposing. So this is very easy to, not a big challenging thing to do. So this coil now maybe where it is. So I will draw with this one. So if I draw, so this is V of t, this is V of t, and the coil current. This is the first coil. This is the first coil, and this is the second coil 2, coil number 2, and this is the diagram. See now this is V of t, no difference in this, and this is I, that is also not a difference, and this is I1, that is also no difference, and this will be I minus I1, no difference, no difference. This is L1, this is L2, and whatever you have here, mutual M, mutual inductance. See this one is dot now, and this is dot. So what happens here? Current is entering, current is leaving this coil, so this is opposing. This is opposing. And if you do whatever we have done here, write the KVL expression, and you need to find what is L equivalent value. That is the whole idea. So if you do so, you will get V of t will be is equal to L equivalent of di by dt. That is the whole idea. And you will get L equivalent will be is equal to L1, L2 minus m square divided by L1 plus L2 plus 2m plus 2m. That is the uh, equation. This is the equation you will get if it is series, parallel opposing. This is for parallel opposing. Try to understand, right? You do this by yourself. And verify it. If you have any doubt, please post it in the comments. I will reply for this one, right? So we have seen what are the topics we have seen today. We have just taken the basics of coupled coils, right? We have gone for how to write the expressions of KVL expressions for a coupled coils connected in series, and first one is aiding, and the second expression we have gone for series opposing, and then we have came into parallel. If two coupled coils are connected in parallel, and if it is aiding, then what is the equivalent inductance of the circuit? That is what we have found, and I have let you to find what is the value of L equivalent, that is equivalent inductance in the circuit if two coupled coils are connected in parallel and opposing each other. I've given you the answers, and you try to do by yourself, right? We will see in the next class with the numerical problems. We will go for the numerical problems, and then we will see how to write the expressions, right? Thank you.